Okay, so what I want to give is I want to give a non-commutative geometric classification result which is due to my advisor, Yuri Beres, and his collaborator, Oleg Chalik. Okay, and so let's introduce the geometric object of interest. So X will be a smooth, affine, irreducible curve. Okay, and once we have this smooth, affine, irreducible curve, we can consider its global sections. And from that, we can produce the ring of differential operators on X. And maybe I'll emphasize, because Hannah's just been talking about the derived category, differential operators via the D. Okay? Okay, so we're interested in classifying isomorphism classes of left ideals of D of X for this smooth affine curve. And I'm going to call the set of such isomorphism classes, I'm going to call it J of X. Okay? Now I need an observation. Okay, if I start with an ideal, a left ideal inside of this ring, now D of X is a hereditary domain, so this ideal is in particular projective. So I can consider the K-theory class determined by I inside of K0 of D of X. Okay. But now there's a theorem due to Quillen, which says that when you have a nice enough filtered algebra, that the K0 of the filtered algebra is the same thing as K0 of the zeroth graded piece. So this abelian group is isomorphic to K0 of just the curve X. Okay. And now we know, sort of standard algebraic geometry, that K0 of X is isomorphic to pick X cross Z. So the map is rank cross determinant, but the other way around. So maybe I can have botched that up, but I don't want to fix it because I don't have time. Okay. And in particular, if I start with an ideal, the class in pick X will, the class I get here will be rank 1. So sort of, let me combine these maps. I have a map gamma, which starts from an isomorphism class of ideal, and it lands me inside of pick X. Okay. It's in some isomorphism class of ideal. Okay, to something here. I just want to name the map, lambda. And I'm going to classify isomorphism classes of left ideals of X with some fixed target inside of the codomain of lambda, right? So I'm interested in describing the preimage of some line bundle on X, right? Okay. So I mentioned already that the ring of differential operators is hereditary. And in our classification result, we're going to be inspired by the only other big class of hereditary algebras, quivers. So if I have a quiver Q, so here's a quiver. One thing I might form is the path algebra of the quiver, which probably everyone has seen. It's a free algebra with composition of paths as the multiplication. But there are things I might do to this quiver first before forming the path algebra. One is framing. And by that, I mean I'm going to add a new vertex and a new arrow from the new vertex to one of the odd ones. So for the example I've drawn, framing would look like this. Here's a new vertex, I'll call it infinity, and I add a new arrow. The other construction that's common for quivers is forming what's called the pre-projective algebra. okay? And how does one form the pre-projective algebra? You have the same vertex set, you double with arrows, you add no arrows going in the opposite direction, and you add relations, one at each vertex. So my pre-projective algebra would have 2 arrows here. So if I call this one x, it would have x and x prime, the original arrow, and one backwards, and I have to add a relation in, which I'm not going to say, but you may have seen it. Okay? I'm going to suggestively call K of QA. And so I'm going to use these constructions standard for quivers to describe the ideals of a ring of differential operators. So now I'm going to take my A to be the ring of differential operators on my smooth curve. How do I get the ideals? So let's do the same thing. First, we're going to frame A. It's not a quiver anymore, so I need to describe it algebraically, what my framing means. And in fact, it means the following. Yeah, shoot. I put the, I'm going to define a new algebra, which will be framed A. So I put functions on x in the top left of a matrix ring. I put any projective module of x I like. I'm going to leave the bottom left empty, and I'm going to put the ground field here. Okay? And I claim if you substitute A equals KQ, you get back the framing from before. Sure. And then I want to form the pre-projective algebra. Okay, and I'm going to apply it to B. And so how do I do this? Let me just tell you that I take the tensor algebra of B of some derivation module. So this is derivations from B into B tensor B. It's a bimodule, so I can take the tensor algebra, and I have to add in a relation, the same as for the quiver version of a pre-projective algebra. So both of these constructions make sense abstractly, okay? And then in my last minute, I've just heard the ding. Let me tell you the classification result. So the theorem is the following. It says there exists a set theoretic bijection okay, from the disjoint union of the representation varieties of this pre-projective algebra here with some fixed dimension vector. And this is in bijection with the set of ideals for some fixed projective line bundle, like before. And this union is over lambda common n. Yeah, sure, I'll stop there and take questions.